For Module 5, we're looking at aqueous equilibria, A-Q-U-E-O-U-S, aqueous equilibria. And specifically what we're looking at buffer solutions. That's one of the definitions you should have is buffers. And we're looking at titrations, be able to define titration between like weak acids and strong bases. And actually, I'm going to give you some problem solving tips down here in a minute. But equations you're going to need to remember from the previous module, pH equals the negative log log of the concentration of the hydrogen ion. And we have the Nernst equation. pH is equal to pKa plus the log log of the conjugate base over the weak acid. So pKa is the negative log log of the Ka. Now, the Ka should be tabulated or given to you. So, other definitions you might need to know what an indicator is and how to choose the correct indicator for a titration. Also, what are the factors that affect solubility? Things you should remember: when can a calculation be simplified? You should remember how to balance equations. You need to make sure that you can read those solubility rules and know what are strong acids and strong bases so that you can tell if you have a weak acid or a weak base. You should also know what it means in a KSP. This isn't exactly constants and variables, but in a KSP situation, what does it mean when Q is greater than KSP? When Q equals KSP, that's supposed to be a P. And what does it mean when Q is less than KSP? In one of these, you will have a precipitate, and the other two you will not. So which is which? Remember, making a precipitate means a solid is coming out of solution. So I told you I was going to have some problem-solving tips as well. This is really focused on the weak acid strong base titration. So before we can decide where we're going to go with our problem solving, we need to know what is the equivalence point. So the first thing we do is find the equivalence point of our titration. Now you need to have that balanced chemical equation first. So balanced equation. And then you're going to calculate that equivalence point. And how you're going to do that is you're going to take, let me resize that again. You're going to take the volume of the acid in liters, and you're going to multiply that by the concentration in molarity. So it's going to be moles of acid per 1 liter acid. So this is the concentration of the acid specifically. Now we use that balanced chemical equation. We're using that stoichiometry. So we need the moles of the base that react with moles of acid. So again, this is from that balanced equation. That's where we get that. Then we're going to use the concentration of the base that we have, and we're going to flip it upside down so that liter is in the numerator. 1 liter of base has how many moles of base? Again, that is the concentration. It should be given to you. And what you should end up with then is the liters of base at the equivalence point. So from here, you can decide, are you before the equivalence, at the equivalence, or after the equivalence? Then we can calculate the pH. So before the equivalence point, we'll start with before EQ. What we're going to do is we're going to find how many moles of acid to begin with that we have, and we're going to subtract the moles of base because that's what's going to react. You'll have to multiply stoichiometrically if you need to, but 99% of the time in my class, it's going to be a 1-to-1. So we're just going to go with this way. You're going to calculate your moles of acid, calculate your moles of base, and subtract, and you will have a leftover moles of acid left. Let's see if I can move this a little bit so that my hand doesn't have to be off the screen. Then we can find the pH by using that Henderson-Hasselbalch equation, but we can just adjust it a little bit. So you're going to need that pKa, and you're going to, I forgot the log log, and then we're going to take the ratio. We're going to have the moles of base from right there, and then we're going to divide that by the moles of acid left. So let's see if I can give this a highlight so that you can see this. So the moles of acid left are here, and the moles of base value here, and you should be able to calculate the pH that way. So at the equivalence point, this is the tricky part. So at the equivalence point, you're going to take the moles of acid you started with, and you're going to divide that by the total liters of solution. And we're going to call that the concentration of A-, because everything's going over and making that conjugate base. Then we need the equilibrium. A- plus water is in equilibrium with our weak acid and hydroxide solution. So initially we have this concentration of A-, which we got from here. And then we'll have some change where this is going to be, we're going to take some value x away. We will add a value x to both of these so that at equilibrium we have A-, minus x, x, and x. So now what we have, this is a base equation, so we need the Kb, and you might want to define Ka versus Kb. And there is an equation up here as well. So Kw should be equal to Ka times Kb. So, okay, Kb is then equal to x squared over the concentration of A- minus x. So you solve for x. X is the concentration of OH minus. So you can find POH, then you can find pH. Okay, because pH equals 14 minus POH. So that's how you find the pH at the equivalence point. Now, after the equivalence point, please work a lot of these problems. You're going to start with the moles of base that have been added, and you're going to subtract the moles of acid that are there. And what you have left are moles of base left. That is in excess. So the concentration of the hydroxide ion in this case is going to be moles of base left divided by total volume in liters. Then you can find the POH, which is the negative log of the hydroxide ion, and the pH is then 14 minus POH. Okay, so that is how you can find the pH at various points in a titration of a weak acid and a strong base.